bound state condition.
What is the criteria for a function to become a bound state solution?
Yes, sir. Yes.
See, normally there are certain criteria for a function to become. I hope you're asking a solution to some Schrodinger equation, right?
Yes, sir. Yes, sir.
Yeah. So we have to understand the derivatives of the wave function. And of course, the derivative of the wave function should also be continuous at all points where the potential is finite. So this continuity of the derivative of the wave function can only be compromised only those points where the potential itself goes to infinity. Okay, so that's all. They are all the only conditions. Suppose if you don't, you're not looking for a bound state. Suppose if you think of some scattering states, then the wave function need not go to zero at infinity because it is usually an oscillatory function, a plane wave, which will not go to infinity at extends to infinity or extends to minus infinity. That is fine. But if it is a bound state solution, then it has to go to infinity. It should not be there everywhere. If it is bound means it is bound in some finite volume.
Sir, suppose a function like exponential minus r divided by r cube. Is that a solution of a bound state solution?
Exponential minus r divided by r cube.
Yes, sir. As r tends to infinity, it will be diverged, right?
Yeah. So when you have some function like that, then you have to understand that whenever you have a product of two functions like this, one is 1 by r cube and e to the minus r, right? So you have to ask a question in different asymptotic regions, which function will have a dominant behavior? Okay. So when r goes to infinity, it is e to the power minus r that dominates. Okay. And you can understand why, because e to the minus r can be written as 1 minus r plus r square, like that, right? So you will have all powers of r will be there in e to the minus r. And hence when r is very large, it is e to the minus r that dominates compared to 1 by r cube. So as r goes to infinity, e to the minus r by r cube will also go to infinity. It is not only in this case, whatever is the power, e to the minus r divided by r power n for any finite n, it is e to the minus r that dominates in the limit r goes to infinity. When r goes to 0, this will go to infinity because e to the minus r will be simply 1 and 1 by r cube will take this to infinity. So this will diverge only in the limit r goes to 0. Whereas r goes to infinity, it will converge. Okay. Now you ask a question, is it allowed? As r goes to infinity, this divergence, as r goes to 0, it diverges, but is this divergence allowed? Okay. So sometimes we can say that this divergence can come because of some singularity at the origin. That means there can be some delta function like a source at the origin. Then you can say that this wave function can diverge at that point. Okay, so so that is what this is. So essentially, when there is a singularity at the origin, you have to ask a question: what happens to this function at a point just outside the origin and everywhere else.
Sir, for delta function, we have a cusp, right? Like the wave function should be continuous at the boundaries, and its derivative should not be continuous. May not be continuous because there is a discontinuity. There is a like infinite discontinuity. So there is a cusp, but can the wave function have this infinite discontinuity? Like it can it diverge?
Um, okay, so let us try to understand this. So, the question that you're asking is that if just 1 minute. So a function from f of r is equal to e to the minus r divided by r cube, right? So what is the question, Paresh? What the question is this?
Yes, sir.
Can
Is
this
this
be
a solution to bound state under bound state condition?
okay? Can this be a bound state? Okay, so f of r going to 0 as r goes to infinity is, this is clear because e to the minus r dominates as r goes to infinity. Okay, and so this is, so at infinity. So what happens as r goes to 0? R goes to 0, f of r goes to infinity. So if you are plotting this as a function of r, this goes to infinity, this goes to 0 as r goes to, so it will be like this. Now the point is that so can we, so the question is, because of this, what happens at so mod square f of r mod square into r square dr. So when you take an integral from 0 to infinity, so this one is equal to integral 0 to infinity e to the minus 2r divided by r to the 6 to r square dr. Okay, so this because this r square will cancel with this and you get r for 4 here. So as r goes to 0, this r power, there will be a denominator in every possible answer that you get for this integral, and it diverges. So this function cannot be normalized. this function cannot be normalized. But instead of this r cube, if you have r, okay, suppose you have e to the minus r by r. Suppose if you have a function like this, then what happens? This r square and this r square will cancel. Then you can normalize that function. Okay, so this cannot be a wave function because we will not be able to normalize it. The total probability this integral has to be finite so that the normalization will give you the total probability to be 1. So this wave function we will not be able to normalize in this region. Of course, r is a radial coordinate and it varies from 0 to infinity. So in this region, this does not admit normalization because this integral is divergent. So the answer for this is no. It cannot represent a bound state. Is that okay?
Okay, sir. Thank you, sir. Okay, sir.
Sir, I had the doubt in the same question, and for this, the answer given for the question was means the allowed wave function for the particle in bound state is given as n e raised to minus alpha x e raised to minus beta into x square plus y square plus z square.
Just 1 minute. Say that again.
N e raised to minus alpha x into e raised to minus beta into x square plus y square plus z square.
Okay, so this is given as your wave function.
Yeah, this is the correct answer for the bound state. Can you explain how this is coming also, sir?
Okay, so this is fine because you see it is like n e to the minus alpha x into e to the minus beta x r square, correct?
Yes,
x
sir.
plus y square plus z square is r square. Or you could have also written as n e to the power minus alpha, and write this as r sine theta cos phi. That is the value of x. X is r sine theta cos phi in spherical polar coordinates. Beta r square. Okay. So now you can say that so this function. Okay. So now I should write this as psi. Now I'm writing in terms of r theta phi. Okay. So you can see that as r goes to infinity, this will go to 0. Psi as r goes to infinity goes to 0, and psi as r goes to 0 is n, constant. It doesn't diverge, and you can normalize this one. Okay, you can normalize this because both are minus signs, so this can be normalized.
Yeah.
So this is
yes, sir.
This is an allowed bound state.
Thank you, sir.
Yeah.
Sir, I have another question also, which I couldn't understand fully.
Yeah. Go ahead.
Okay. The question is a one-dimensional simple harmonic oscillator with Hamiltonian H0 is equal to p square by 2m plus half kx square is subjected to a small perturbation h1 is equal to alpha x plus beta x cube plus gamma x raised to 4. The first order correction to the ground state energy is dependent on. Yes, sir. Yes, sir.
Okay, so this is your H prime. First order correction for what?
First order correction for the ground state energy is dependent on. The options are only beta, alpha and gamma, alpha and beta, and only gamma.
Oh, it depends on, you are asking. It depends only on gamma.
Yes, sir. Yes. Sir, can you explain why, sir?
That is because you see, your if you can remember that operator method that you have used, okay. So you remember this X operator is proportional to A plus A dagger. Okay. Or maybe I can also use this slightly. Okay, if you let me, I will come back to this, but let me give you a simpler argument. You know, first order correction in this case for the ground state is given by, if I have to write integral minus infinity to plus infinity psi 0 star of x into h prime into psi 0 of x dx, correct? Because first order correction is just the expectation value of the perturbation Hamiltonian with respect to the state, in this case ground state. Now notice that this is an even function of x. So is this, correct? Because what is psi 0 of x? Psi 0 of x is simply a Gaussian minus x square by some alpha x square by 2, something like this, right? This alpha and this alpha are not same. So let's say some 2l square, something like that. It's a Gaussian, so it's an even function of x. So this product is also even. So those terms which are odd functions of time, odd functions of x, will make this entire integral odd function of x. You follow that, no?
Will make the. I didn't catch the last part, sir.
See, what I am saying is, this is nothing but, this is minus infinity to infinity, psi 0 of x modulus square into h prime, correct?
Yeah.
So this h prime is your alpha x plus beta x cube plus gamma x to the power 4. Now this is an even function. I can write this as three parts of the integral, no? One with x, one with x cube, other with x. So x is odd function, because x going to minus x, it will pick up a minus sign. So when you multiply this and this, x into this one, the total integrand will become odd function. Same story with x cube also, because x cube is also odd. And you know, this is a general result that if you take minus infinity to infinity, f of x dx is equal to 0 if f of x is an odd function. If f of x is equal to minus f of x. So this is a general result, no?
Yes.
So because of that, integral with x cube will go to 0. Now x power 4 is even function, and hence x power 4, that integral will be non-zero.
Yes.
So that is okay. So let me also give you the other argument, which may be useful in some other problems. So we know that this x is proportional to a plus a dagger. Okay, a plus a dagger. Now, when you are trying to take E01, the first order correction, okay, so that is going to be equal to, in this Dirac notation, it is 0, h prime, 0. So now if you ask what happens to, this is in, so whatever I am, so the above argument is also, okay, so this argument is also, this argument, they have asked for the ground state. Suppose if they would have asked for the first excited state, will your answer change?
Yes, sir.
What will be your answer if they would have asked this question for first excited state? Same question, instead of ground state, if they asked you to find out first order correction for the first excited state,
I don't know, sir.
no. What I'm saying, if you understood this argument, you can follow the same route. No. What is the difference between ground state and first excited state?
So the function will be little different.
Function is different, but we are not really going to substitute the function
So
here.
mod square the mod square will be even function, sir.
So even for that, it is even function.
Yes,
No?
sir. Won't change.
Psi1 of x is an odd function, but mod square will be even function. So there is no difference. Whether it is first excited state or ground state, as far as this Hamiltonian is concerned, the first order correction is going to be only contributed by this gamma for all states. You follow that? Because this is going to be even, that mod psi square is going to be even whether psi is even or psi is odd. And all the eigenstates of Hamiltonian of harmonic oscillator are either odd or even. That is because the Hamiltonian itself is an even function. There is a parity symmetry for the Hamiltonian. Correct? Because you have x square term, x going to minus x does not change the Hamiltonian. Because of that, the eigenstates of Hamiltonian are also eigenstates of parity operator. Parity operator has only two eigenstates, either even parity or odd parity. As a result, whatever is whether they ask for a ground state or first excited state or nth excited state, the answer is going to be same. Only gamma will contribute. Beta and x, first order correction, they will always be 0. Okay, is that clear?
Yes, sir.
Yeah. So, once you understand that, then this argument is also going to give us slightly say, it is, I don't know which argument is easier, but let me present this argument also. So suppose you are interested in asking a question, what is 0 x operator 0? Or let me now generally write, suppose let's say there is some n operator here, because n x operator and n here. It's not ground state, but some nth excited state. Now this is nothing but, so this is proportional to, I'm not writing this proportionality constant here, so that's what I'm saying. This is proportional to n a plus a dagger n. Now what happens? This will be equal to n. So when a is acting on n, it will become n minus 1 plus n. When a dagger is acting on n, it will become n plus 1. Of course, there will be some factors here. Okay, so that will be root n here and root n plus 1 here. So those factors will be there, but doesn't matter. These are orthogonal states. So n with n minus 1 is 0 and n with n plus 1 is also 0. And hence, this will be 0. So this is true for, that is, n x operator n is equal to 0 for all n. Whatever is the state, this is 0. Now you can ask what is n x square n. X square n. That will be equal to n a plus, I'm not writing, so please don't take this as a rigorous calculation. I'm not writing all those constants. So that is given by this. This calculation, I'm sure you might have done it earlier. So this will be nothing but n a square a dagger plus a dagger a plus a dagger square acting on n. So that will give you n with n minus 2, which will be 0, plus this will make this n plus 1 and this will bring it to n. So there will be one n term here. Okay, that is coming from here. And similarly, there will be an n term here that is coming from here. Of course, the coefficients will be there that you have to find out. Plus, this will be n with n plus 2. So this will be 0, this will be 0, but this will be non-zero. These two terms will be non-zero, and hence we can say that n x square n is not equal to 0. Okay, so this is non-zero. Now you can argue that n from x to the power m n, if you ask a question, this is equal to 0 if m is odd. Same argument, of course, because if it is odd, you are going so a dagger. So one rising, one lowering, like that it will not be there. It will always be two rising, one lowering, like that only it will be there, and hence they will give rise to different state whose inner product will kill that one. So this is another argument to say that only the even powers will contribute to first what is called first order correction. This Hamiltonian.
Yes, sir. Thank you, sir.
Yeah.
Sir,
Yeah.
sir, I have a question. Two electrons at fixed positions on the z-axis have a magnetic dipole-dipole interaction energy E is equals to S1 S2 A equal to A times S1 S2 minus 3 S1Z times S2Z, where Si equals to half of sigma I being Pauli spin matrix. A is constant, E by A in terms of total spin operator S equals to S1 plus S2 is.
Okay, so let me write down what okay, so tell me what is the two electron spin z-axis.
Z-axis, fixed positions on the Z-axis have magnetic dipole-dipole interaction energy. E is equals to A, capital A, times S1 times S2 minus 3 S1Z times S2Z.
Okay.
Whole within brackets, sir. A times whole.
Okay.
Where Si equals to half of sigma I.
Okay. So this is
Pauli
a
spin
vector.
matrix.
This is a vector,
Vector, yes, sir.
and this one is S1 dot S2.
S1 dot S2.
Okay.
A is constant. E by A in terms of total spin operator S equals to S1 vector plus S2 vector.
E by A in terms of total spin operator S is equal to
S2 vector.
1 plus S. So they are asking they are asking the value of E by A,
Yes.
no? So it will be in terms of some H bar and things.
The options are a square minus 3az square.
S square
Minus 3az square. The option B is a square minus 3az square by 2. Third option is a square. And option D is a minus 3az.
S minus 3S. Okay. Okay, so from here you can write that Sz is equal to S1Z plus S2Z. Okay. So, Sz square can be written as S1Z square plus S2Z S2Z square plus 2S1Z S2Z. So that means our S1Z S2Z can be written as Sz square minus S1Z square minus S2Z square divided by 2. Okay. So then we have the other case is that when you write down S square, it will be S1 square plus S2 square plus 2 times S1 dot S, that level. So S1 dot S2 can be written as S square minus S1 square plus minus S2 square divided by 2. Okay, so I can write this S1 square as S1x square plus S1y square plus S1z square. Similarly for 2. So if I write down this E by A is equal to, so there is a half here and half here, so let me pull that out half. So S square minus S1x square minus S1y square minus S1z square minus S2x square minus S2y square minus S2z square. That much is over with this minus 3 times, right? So 3 times Sz square plus 3 times S1z square plus 3 times S2z square. Okay. So, so I can write this. I can write this. This much I can write this as. So I can write this 1 by 2 into S square minus S1 x square plus S1 y square. I can write this as S1 square minus S1 z square. Okay, so that is what we have come from. So you can see minus S1z square plus 3S1z square is 2 plus 2. So we have minus 1x square 1y square plus 2 times s1z square two times s2z square minus 3 times sz square. So I can write this. This part s square is here and 3sz square is here, so let me write them. Then I have minus s1x square.
Sir, the Pauli spin matrix will be useful or something like. Will it be useful? Like SI equals to half sigma.
But I don't know where it will be useful.
SI equals to half sigma.
Okay. Okay, I think you are right. So, yeah, I think we have to use that one. So, you have S1x is sigma 1x, right? So, its square is 1 by 4 times sigma 1x square. So, that is identity. Sigma x square is identity.
Yes, sir.
So, then we have, okay, so we use that one. Then we can say that this is equal to half s square minus 3sz square minus 1/4 identity minus 1/4 identity plus 2/4 identity minus 1/4 identity minus 1/4 identity plus 2/4 identity. So this will be 0, correct? This is 1/2 and this is these two together 1/2. That will be equal to s square minus 3sz square divided. That is there, right, in the option?
Option B is the answer. So I have mentioned this problem because I'm not very comfortable with spins. So like questions on spins, I find it difficult to tackle.
This is essentially that we discussed this one when we talked about addition of angular momentum.
Yes, sir.
When we add them, then we have to convert in terms of the total spins.
And so I have one more question. A one-dimensional box with width L, capital L, contains two spinless particles, each of mass small m. The interaction between the particles is described by a potential energy V of x1 x2 is equals to small a times delta x1 minus x2. The first order correction in energy is the four options are 3a by 2l.
This is in the spinless particles. ground state.
Spinless in the energy, it's not written, like maybe ground state energy, it's not written. The ground state was not. Maybe ground state. Question, there is no mention. It's not mentioned.
Yeah, so that if it is in the ground state, see they are spinless.
Yes, sir.
So both of them can be n is equal to 1. Okay, so two particles are there. So you will have your ground state energy is 2 by L into sine pi by L into x. It's 1 into sine pi by L into x2. Okay, so this is your ground state energy. Psi 1 of x1 comma x in particle in a box. Here,
Okay, so I didn't understand this actually. Because it's
yeah,
one-dimensional
one-dimensional
box.
box, but there are two particles. So it is going to be phi 1 of x1 into phi 1 of x2. Both are in the n equal to 1 state.
Okay. So if they're distinguishable then?
Yeah. So
If they're
basically,
distinguishable,
once you say you have spinless, then that means there is no boson fermion difference, right? So you have to consider them.
spinless means spin zero, sir. So
Yeah.
spin zero.
So both of them can be in the ground state. That is what I am telling. See, your
Yes, sir.
particle in a box has these levels. Now both particles can be in the ground state.
Okay, sir.
Since they don't have spin wave function, then this is the wave function. That's all.
Okay, sir.
So this is going to be your wave function. Now you have to first order correction is simply integral 0 to L. Okay, so this is psi 1 of x1 comma x2 modulus square into v of x1 comma x2. Correct? So this is the expectation value basically, because this variable is only in terms of x1, x2. I wrote it like this. Otherwise, you have to write wave function psi star v psi like that. So that is equal to, we have 4 by L square into integral 0 to L. Of course, you have to do integration dx1 dx2. So we have sine square pi by L x1 and sine square pi by L x2 into, so A I will put outside, and delta of x1 minus x2 or dx1 dx. So one integral you can use delta function. Let's say we integrate over x2, so I have 4a by L square. The integral, both of them are between 0 to L and 0 to L. So one integral is dx1 and sine. If you put x2 equal to x1, then this will be same as this. So it will be sine to the power 4 into pi by L into x1. So this integral you have to do. What are the answers you have?
So 3a by 2L.
3a by
2L. Option B is a by L. Option C is a by 2L. And option D is 3a by L.
3a by L. Okay, so you have to do this integral. How do you do this integral? You can write probably sine 4 theta. What is sine 4 theta? Is sine 2 theta plus 2 theta. You can write it as sine 2 theta cos 2 theta plus this is basically cos 2 theta sine 2 theta. So that's equal to 2 times sine theta cos theta into cos square theta minus sine square theta. So then we will have 2 sine theta cos cube theta minus 2 sine cube theta cos theta. So that is we can write this so 2 sine theta okay, so I think before coming here itself we can write this as 1 minus sine square theta. So this becomes 2 sine theta cos theta into 1 minus 2 sine square. So that is equal to 2 sine theta cos theta minus 4 sine cube theta 4 sine cube theta. So this I can write it as 2 sine 2 theta minus 2 sine cube theta 2 sine square theta into sine 2. So that is what we have started with. Of course, the aim is to bring everything in terms of thetas. 2 theta, 3 theta, like that. So we will, let's come to this sine 2 theta into 1 minus 2 sine square theta. So let's start from here. Sine square theta okay, so let's write this as sine 2 theta minus 2 sine theta, so that will be sine cube theta into cos theta. Sine cube, that is 4. Okay, so sine cube theta, so sine 2 theta plus theta, that is equal to sine 2 theta cos theta plus cos 2 theta sine theta. So that
Sir,
is, yeah.
sir, for sine cube theta, we can take sine theta equals to t, then we can dt equals to cos theta d theta. We can we do that?
So from here,
Sine cube theta, if we can take sine theta equal to t, then we can get dt equal to the cos theta d theta.
let's see. So let's substitute that in the integral. Okay, so we have first order correction is equal to 4a by L square, integral 0 to L. We have sine 2 times x by L, 1 by L dx1, minus 16a by L square, integral 0 to L, sine cube x by x1 by L into cos x1.
So pi is there, I think. Pi.
So this integral is cos. So this is the first one is 4a by L square into L by 2 pi into sine becomes minus cos 2 pi x1 by L from 0 to L. So here 16a by L square. So you can write t is equal to sine cube by x1 by L and dt is equal to pi by L. Sorry, t is equal to this one. So pi by L cos pi x1 by L dx1. And so this will, of course, we have to worry about integrals. 0 is 0 and L is, I put L sin pi. Sin pi is also 0. Let's keep it like that. Then we have t cube into dt. Of course, there will be a pi by L, right? And this will give you t to the 4 by 4. So I can write that as sine to the power 4 pi x1 by L by another L by pi x1, L by pi, and that L by pi will cancel with this L by pi anyway. And then I have to do some zeros to this L. So this anyway goes to 0. So here what we will have is, if I put L, this is minus cos 2 pi minus cos 0 cos 0 is 0. So this is also 0.
So there might be a mistake in the question.
Yeah, but I think this is a standard question. It is there in the Sakurai's modern quantum mechanics exercise problems in identical particles chapter. Our perturbation chapter. One of these chapters, this question is there. Okay, but anyway, please check this. Up to this, everything is fine. Only thing is we have to carefully do this integral.
Yes, sir.
So
Up to
check
that, things correct.
Yeah. So please try that integral. So do you want to spend some time preparing and then we have this discussion afterwards?
Yes, sir. So on 6th we have the exam,
Uh,
so we
So
don't
we-
have much time.
yeah, so but if you don't have much doubts, then it will be also time consuming to have this online meeting, no?
Yes, sir.
So maybe we can meet tomorrow at same time, and if you want if you think you will be ready with some questions, we can meet tonight. But I think there is not much time.
Okay. Yes,
Are
sir,
there
can
any
you,
way you can get
how-
ready?
sir, can
Yeah.
you tell us that how much score is like enough for gate? Like how much should we attempt for gate?
Actually, uh, frankly speaking, I did not follow the pattern of this gate for a long time.
Okay.
So I really don't know what for how many. At least I knew it in CSIR, but I did not know what is the number of questions, how many marks. I have no idea. For a long time, I did not look at gate question.
Okay.
So that way, but the thumb rule is that like 50% of the marks, if you are getting, then you will get reasonably good rank.
Okay.
That's what is a thumb rule, which is probably same in other exams also. For example, the score in just like exams is much lower.
Yes.
Sometimes if you
Cutoff
get
is very low.
very low, yeah. But gate, I think 50% of the marks if you get, you will get reasonably very good rank.
Okay, sir. Thank you.
Hello, sir.
Yes, Asha.
Sir, can I ask a simple question on tensor?
Yeah.
Okay, sir. So the question is, let Vi be the ith component of a vector field V, which has zero divergence. Dou j is equivalent to dou by dou xj. The expression for epsilon ijk into epsilon lmk, dou j dou l Vm is equal to.
Okay, I should tell you that I did not listen completely because
Sir, I can repeat.
yeah, but your audio is discontinuous at times, so I really did not listen it continuously. Okay, can you maybe you can speak slowly so that I can write.
Yes, sir. I'll. Sir, let Vi be the ith component of a vector field V,
Ith component of vector field V.
which has zero divergence.
Okay, zero divergence.
If dou j is equivalent to
Uh,
dou by dou xj,
uh,
the expression for
for
epsilon ijk into epsilon lmk
LMK.
is dou j dou l Vm.
Okay,
Dou l,
VM.
yes, sir, is equal to. That's the question.
Oh.
Sir, you need options.
Okay, tell me.
First option is minus dou j dou k Vi. Second option, dou J, dou K, Vi. Dou J square, Vi. Third option, sir.
So this square will be,
And fourth option is minus dou J square, Vi.
okay, so
So it's transformation rule, I think so. It's a transformation rule question, sir.
But you know that some basic rules that we probably you are familiar with our discussion in electrodynamics. So if you have a vector A, okay, so let's say you have a vector A, this is represented as AI. This is called free index. Okay, so in this index notation, you represent this as AI. Now you can define A dot B as simply AJ BJ. Okay, so this index is called dummy index because it is repeated. Okay, this is called dummy index, repeated. Then because it is repeated, it is summed over. Okay, so this is basically A1 B1 plus A2 B2. Because this J will take all values 1, 2, 3. It is called dummy because I can write this as AJ BJ or AK BK, whatever it is. Whereas here it is free, so AI means if I write A1, that is the first component. A2 means there is second component. So there is some kind of a meaning for this index, whereas this J is dummy index. Then we had defined this these vectors. Suppose if I have A and then cross it with B, A cross B, this is, so let's say I want to write ith component of this one, and that is given by epsilon ijk into AJ BK. This is how the cross product is written. Okay, so this much is this much of definition is enough. Now some properties of epsilon ijk. Suppose if I have epsilon ijk, this is same as epsilon kj kij, which is same as epsilon jki. These are cyclic permutations. Now k is going here in this case, or j is going here in this case. So they are all 1. Okay, so I mean, if it is 1, it is 1, otherwise it is -1. So this is something that you may recall. So now let us look at this expression. Okay, so this expression is epsilon ijk. So let us write this del j outside and then write this one as epsilon klm into del l Vm. Because this Lmk I can write it as KLM. I can take this K here. Now this is, from this definition, it is like a cross product. So this is like epsilon ijk del j into what I can write this? I can write this as del cross V of kth element. Del cross V of kth element. You follow, no? This is del L Vm, like AJ BK. So del cross V of kth element. Now you look at this one. So I can write this also. Okay. So let J and K be there. So there is J here, K here, J here, K here. So this is like another cross product. So this is del cross V. Okay, del cross V of ith element. Because what is the free index? K K is repeated, J is repeated, so I is there. So it is ith element of del cross del cross. But del cross V. Okay, so
gradient to divergence of V minus Laplacian of V.
correct. So this I think they expect you to remember, or you might have used this many times. So this is del square. But they have given that gradient of V is divergence of V is 0. So this term is 0. So this is equal to minus del square into V. So that that is what minus del square V is. This minus dou j square V. Oh, 1 minute. So let us look at del square. Del square is del dot del V, right? So del square V is del dot gradient of gradient of divergence. That is del square. So del square is del dot del. Okay, so del dot del is dou j square. Okay, and V is Vi. That's correct. So the last one is correct. This one is minus dou j square. Is that clear?
Yes, sir.
Okay.
Excuse me, sir.
Yeah. Arshad.
Sir, I have yes, sir. I have doubt in statistical mechanics, sir. Is it okay to ask now?
Yeah.
Okay, sir. Sir, in microcanonical ensemble, we fix energy and then we have an ensemble now, sir. When we fix energy, we have defined a constant energy surface. And we said Hamiltonian will map all those points on the constant energy surface to that constant E. Now I have a question, sir, but it seems a bit awkward to ask, but still I ask, sir.
Very good.
When we fix the energy, we said we create a surface. And now the question is, what if there are only few discrete points in phase space that can be mapped to that constant energy E? What if we don't have a surface and only few discrete points in phase space that can be mapped to constant energy? Instead of a surface, a few discrete points. What if we have a situation like that?
See, I do not know if you are. I am not very sure if I understood your question, but let me see if I can try to understand. So
should I repeat, sir?
No, I understood what you said, but I'm trying to understand what you have in mind in asking this question. So essentially, if you are thinking of classical systems, where you can write down a Hamiltonian classical systems what do I mean? You have position and momentum which are continuously varying, and energy also is continuously varying, and you have a phase space, and there is no uncertainty. All this is assumed when I say you have a classical system.
Yes, sir. Yes, sir.
So in that case, you will have a continuum of points in the phase space. Even if you take a constant energy, there will be continuum of states. So energy surface is
A continuum.
defined in that classical system.
Yes, sir. That's where I have a doubt. What if we don't have a continuum and only discrete points?
Correct. So that kind of situation will come when you take, for example, a quantum system. Then your energy is not continuous. You have only some discrete levels. So the parallel to constant energy surface when your energy is discrete is that a given energy has certain amount of degeneracy. The number of microstates with the same energy corresponds to the degeneracy of that energy. Correct. So that will not be continuous, but it will be also some discrete number of states. So when energy is discrete, when you have only discrete set of points, you are only going to count that one.
Okay, sir. Okay.
So that this continuous energy spectrum is now replaced with a set of degenerate states. This continuous energy surface is replaced with
No, sir. In classical systems itself, I'm asking this question, sir.
Yeah. So in classical,
what if we don't have a continuous surface, only discrete points that maps Hamiltonian to E?
yeah. So what I'm saying is, if there is some constraint based
Yes,
on
sir.
which you don't have it, this one, then you can see this continuous surface is only a classical approximation, right? So it's not that your formalism of microcanonical ensemble does not depend on this one. In fact, if there is no continuous surface, it is much easier to do microcanonical ensemble. So if there is, for some reason, you don't have a continuous surface, then you are a much better situation. You can simply count whatever the number of states by
Yes,
some
sir.
counting technique.
Yes, sir. And also dynamics will take place between only those
Exactly.
discrete points.
Exactly. So there's the microscopic dynamics will only take place in terms of jumping from one microstate to other microstate.
One point to the other. And
correct.
Okay.
See, one example that we can think of is that suppose if you imagine that you have got a long polymer, and then this polymer is put in some kind of a fluid, some solvent, then this polymer can take different configurations, right? So the set of all configurations of this polymer is not continuous in some variable. They are only discrete set of configurations, correct? So that means if you are looking at your, suppose you fix your energy and you ask what is the number of configurations that this polymer can exist, that is going to be discrete set. And
yes.
And when you put this in, suppose you, let's say, assume that you are able to enumerate all those configurations, and then you put this in the solvent, then this polymer configuration keeps fluctuating, changes, and this dynamics will be such that it will jump from one conformation to the other conformation.
Okay, sir. Okay. I had this question because discrete points also form a subset of phase space, no, sir?
Correct. Yes.
So I thought, why not continue discrete points?
Yeah, so continuum is not very serious thing. Continuum is, in fact, we have to deal with continuum only in classical because that is a kind of a baggage from our classical mechanics. But that is not a requirement as such for this theory.
Okay, sir. Okay. Okay. Sir, also one more doubt, sir.
Yeah.
Sir, when we defined grand canonical ensemble, we had three variables now, sir. One is chemical potential, volume, and temperature.
Yes.
And when we did electrons in metals, we finally said that chemical potential is dependent on temperature.
Chemical potential, yes.
I thought that chemical potential, volume, and temperature are independent variables. But chemical potential now depends on temperature for electrons and metals. I couldn't correlate that.
Yeah, so I think, see, this independence and dependence are they they are in the sense that they can be independently controlled. Okay,
Okay,
but suppose, let's say I fix chemical potential, and then I increase the temperature. Okay, then the chemical potential also will change. But increasing the temperature is not the only way to change chemical potential. I can independently change chemical potential. So independent only in that sense in this thermodynamic systems. Like for example, when we say that in canonical ensemble also, you could have asked the same question. We say that we have temperature, volume, and this one. But you know that if I heat the system, expansion takes place and volume changes, no?
Oh, okay, sir.
So that question would have come there also. So the point is that it is not that they will not depend on each other, but you can independently vary them. I can actually, without increasing the temperature, I can increase the volume. And without increasing the volume, I can increase the temperature by pumping some heat into the system. So they can be independently controlled. That's what it means.
Okay, sir. Okay. But if one changes, the other can also change.
Yes, other can also change. So essentially, okay, I think your question is this question is coming from the concept of independent variables in mathematical functions. So if you have a function of x and y, then x and y are independent. It means any change in x will not result in change in y.
Yes,
correct?
sir. I thought exactly like that for temperature volume.
But in thermodynamics, this is somewhat different. That is the reason why, if you look at thermodynamics textbooks, see, for example, in mathematics, when you say dou f by dou x,
yes, sir.
for a function of x and y, when you take a partial derivative with respect to y, okay, with respect to x, let's say, you simply write dou f by dou x. Correct?
Yes, sir.
Now, that means y is kept constant.
Yes, sir.
Correct. Now, in thermodynamics, when you see thermodynamics books, you write dou u by dou t at constant volume, like that. They put a bracket and put v.
Yes, sir.
You notice that, no?
Yes, sir.
Why you specific it?
Other
specific it. Specific for constant volume.
No, every time when you are talking about, let me just show you. So I think, so what I'm trying to distinguish is that when you have a function of x comma y, okay, so when I write dou f by dou x, this means what? This is f at x plus some delta x and a fixed y minus f at x at a fixed y divided by delta x in the limit delta x tending to 0. This is what it is, right? Partial derivative. So here y is fixed.
Yes, sir.
Correct. So now we don't write this as dou f by dou x at fixed y, because this is understood. Correct. If you think that you have
yes, sir.
You have an area, the area is a function of x and y, then you are increasing area only by increasing this one,
the length,
only this x. Then this is basically your dou a by dou x, or you can also increase it by increasing this one. That is only you are increasing y. Correct.
Yes, sir.
X is remain case. So this is how we do it in partial derivatives. But normally when you are trying to look at, for example, let's say you have du equal to TdS minus PdV. Okay, or TDS. Okay, let us keep this. So you want to write down what is temperature, then you say it is dou U by dou S. You write like this at a constant volume.
Okay.
This is because you change your energy and entropy such that volume doesn't change. Only then that will define the temperature. So this additional notation of this one is only to make sure that, because temperature is increasing, volume also change. They are not as independent as you describe in the mathematical functions.
Okay, sir.
They
Okay.
can be independently controlled.
Okay, sir. So by fixing V, we should change S. Then only we'll define temperature.
Correct.
Okay, sir.
The variation of U with respect to S at a fixed V defines the temperature.
Okay, sir. Okay.
Sir, for dou U by dou T, we have specific heat, but if we keep the volume constant, then we have Cv. If we keep the pressure constant, then we have Cp. So
Yeah, but Cp is not dou U by dou
no, dou
T.
H by
Dou H by dou T, because as we discussed, U and H will be changing their roles at constant volume and constant pressure.
Okay, but if we change P instead of V, then will that change? The function will change, because in mathematical functions it don't change.
Yeah, so that is what I'm saying. So when you say you have U will be a function of S, V, and N. Okay, if you can change volume, only then this dou U by dou T at constant volume will give you Cv. But you cannot use this U if you want to change pressure, because pressure will go to enthalpy, which is Sp and N. So then you write down dou H by dou T at constant pressure, then that becomes your Cp. You
Okay,
have to take the right potential, right thermodynamic potential to define. So independent variation will depend on what potential we are using. They depend on independent variation of the parameters. We have to choose the appropriate potential.
so this class has been a reality check for me how unprepared I am for the gate.
Okay. Yeah. So shall we meet tomorrow then? Tomorrow?
Yes, sir. Tomorrow I'll prepare and I'll ask doubts then.
Okay.
Sir?
Yeah.
So if you have little time, can you take one question?
Huh?
So, can you take one more question right now?
Yeah.
Sir, it was about the statistical mechanics that you gave in the semester exam. I was a little confused how to apply. I attempted that question. I don't know it is completely right or wrong. About that carbon monoxide question, occupancy of oxygen and carbon monoxide. Should I read out that question?
What was asked that I don't
Yes,
remember?
sir. I'm reading the question, sir.
Okay.
Carbon monoxide, when present in the lungs, competes with oxygen for binding to hemoglobin. The binding site of hemoglobin can be empty, that is E equal to 0. Oxygen bound, that is E equal to minus 0.7 electron volt. And carbon monoxide bound, that is energy is minus 0.85 electron volt. Now, whenever it is said whenever carbon monoxide is present, that's 0.85 electron volt. Okay, then chemical potential of oxygen and carbon monoxide is minus 0.6 and 0.72. Both of them are minus. Find the probability of oxygen occupying hemoglobin site in the absence of carbon monoxide and in the presence of carbon monoxide.
Yeah.
The probability of oxygen occupying hemoglobin site.
Yeah. So essentially, this is, suppose let's say you have this as a hemoglobin molecule and this is your site. Okay, so this can exist. Normally, carbon monoxide will not be there in the lungs. In the lungs, it can exist as empty state or oxygen bound state. Okay, this is a simplified thing. Actually, real hemoglobin will have 4 sites. Okay, so we're just considering one of the 4 sites. So empty or O2 bond. So if this only is there, then your grand canonical partition function will become 1 plus e to the power minus beta into epsilon, which is minus 0.7 EV, minus minus into minus plus, that is 0.6 EV. This will be your, you have to of course find out body temperature, what is this beta. So this will be your,
take T equal to 310 Kelvin.
In terms of electron volts kBT you calculate, then you get some numerical value for this. Okay, so now probability that oxygen is occupied is given by e to the power minus beta into minus 0.7 plus 0.6 divided by Q.
Yes, sir.
Okay, so that is
now, sir. In this thing, the n value we have taken as 1.
Yeah. So there's only one site
Yeah.
and one molecule that we are.
Yes, sir.
So in presence of CO, what happens is your Q will be equal to 1 plus e to the minus beta into, let's say, EO2 minus mu O2 plus e to the minus beta into ECO minus mu CO. You understand, no? Because this is another possibility. Carbon monoxide is also possible, and then probability of oxygen is same, e to the power minus beta EO2 minus mu O2 divided by, so let us call this as Q prime. It is Q prime. Okay.
Sir,
I exactly I don't remember, but roughly I think this will be something like above 90%. Okay, above 90%, and this turns out to be about some 25% or something. So it drastically reduces the oxygen binding site, oxygen binding probability. This is what we call as carbon monoxide poisoning.
Yes, sir.
Then we will be in danger now, sir.
Yes, this is one. See, that is what I was saying, that when you are exposed to carbon monoxide poisoning, in fact, it is considered to be the most painless death in the entire. I mean, if you consider the set of all possible processes in which one can die, so in that set, this is supposed to be most painless.
Sir.
Sir?
I'm not giving any ideas, but I'm just telling the technical statistical mechanics aspect of it.
Sir?
Yeah.
Sir, when you are calculating Q dash, at that time the sum is over energies also, and also the chemical potential.
Correct.
Right? Like if you're taking over both, then wouldn't there be any cross terms there, like chemical potential for oxygen, but the energy for carbon monoxide?
No, because see, this is what is the power of statistical mechanics. Once you know that these are chemical potentials and these are energies for different species, no, it is the grand partition function is just a product, no.
Yes, sir.
Yeah, so there is no other cross terms.
So that's where I was confused, like whether there will be cross terms or not, or only the terms.
There are no cross terms. It just that is it is like what is called state centric, no.
Yes, sir.
For empty, for oxygen occupation, for this one, and then you multiply. That will be the total grand partition.
Okay, sir. So thank you, sir.
Yeah. I don't know. There were some news reports some years ago that there was somebody who was trying who went to a shopping and then they had a small child, and the child was sleeping, and so they left the child in the car, leaving the air condition on, and they went to shopping, and then when they came back, they found the child was dead. So there were some indications that in the car's air condition, there may be some small leakage of this carbon monoxide gas, and which might have led to this child dying in the car. So carbon monoxide poisoning is one of, in fact, when some fire accident happens, so it's not because of the fire or this thing, it is the carbon monoxide that contains in the smoke that many people seem to die. In fact, this is one such thing that you will not even know that you are going to die.
Yes, sir. Next time we'll be careful with CO, sir.
Yes.
Okay. And not CO2, sir.
Not CO2. CO2 is not
Will
that
not combine with
No, it
hemoglobin.
doesn't. Yes.
Okay, sir. And I also heard that if the hemoglobin
Actually, that hemoglobin, that site where this oxygen binds, there will be an ion, Fe2 plus or Fe3 plus, one ion
yes,
will be
sir.
there, and that is
Or-
what combines with that oxygen, and that also has same a larger affinity to combine with carbon monoxide. That's why that binding energy is more for carbon monoxide, and that is why carbon monoxide competes more effectively with that. And that's the reason why when people say no, that your iron is less in your blood.
Yes. Yes, sir. Yes, sir.
So this iron,
Anemia.
this iron is what sits in those binding sites. I think one hemoglobin molecule seems to have some 4 different, these called heme sites. So these 4 different heme sites, and it's a very complicated story because this binding also depends on, suppose in one molecule, if two or three of them are bound, then there is an acceleration of binding for the other. So it will work like some kind of accelerator or some gear kind of a mechanism is there. So I think it's a very complicated story. But what we are trying to understand is to dilute the story to suit our calculation, so that we get the message and also use grand canonical ensemble, a partition function.
Sir?
Yeah.
So when this that Q grand canonical partition function is written, it is like summation over I and summation over J, e to the power minus beta ei minus mu nj. So when if there is no cross term is coming, that means there is some constraint on that I or J, we can say.
So what that term simply tells you is that you have to simply ask what are the so your that expression simply means that so you are talking about this expression, that Q is equal to sum over I, sum over J, e to the minus beta ei minus mu nc. This term you are saying, right?
Yes, sir.
Okay. So essentially, this is sum over all microstates. Okay. So
Yes,
in a microstate, this microstate has got an energy Ei and number of particles Ng.
Yes, sir.
Correct.
Yes,
So
sir.
in this particular, for this hemoglobin site that we are talking about, so there are 3 microstates. So energy 0, chemical potential 0. Of course, that N is 1. Okay.
Yes, sir.
And
Yes, sir.
energy ECO2, and this is mu O2, and energy ECO, and this mu CO. So this sum over microstates is what we are. Right.
Yes, sir. So I always had a confusion in this, like sum over microstates and sum over the energies. like in canonical ensemble also. Like we have a system where we have degeneracy. Then
Correct.
what we do at that time?
Yeah. So you have to multiply that one with the degeneracy. When you do some more energy,
Means like we are if we talk in terms of microstats, we are adding, like we have three degeneracies, like we are adding all those three, so
correct.
that's why 3 is multiplied.
So you either write this one or you write this one, omega e into e to the minus.
Okay, sir.
So this one you will add so many times. If this is 3, then you add 3 times the same Boltzmann factor.
Yes, sir. Okay, sir.
What about your next semester? Did you get some information about when your classes are going to start or something?
Sir,
No information till now, sir.
calendar it's 8th, sir. 8th of February.
Oh,
But not sure, sir. Previous one, old calendar.
okay.
So we don't know about it.
But anyway, you should get some information to register.
Yes, sir. That will be there.